Hi, this is Ed Kohler with Extreme Networks, and we're back with another installment on our campus fabric architecture. This particular video is going to focus on the use of IP diagnostics, such as ping and traceroute, in tandem with connectivity fault management. I've had a number of requests from different customers and partners to do this, so I thought it would be an interesting video exercise in order to use as the next installment to our series. Now, as we will recall, CFM basically utilized two tools that we had in the previous lab, L2 ping and L2 traceroute. We're going to focus on using layer 2 traceroute here because we're more interested in establishing path behaviors. But keep in mind that the fabric, as we talked about in previous videos, is like a black hole from an IP diagnostics perspective. And this is nice because it takes away visibility and traceroute as a viable tool from a hacker's perspective. But it also takes it away from network administrators. So CFM was designed to bring that tool back to network administrators, and we're going to use that in coordination with IP diagnostics in this video. And really, when we do this, we're going to show how IP diagnostics, such as ping and traceroute, can be used in tandem with CFM. We're going to basically use the IP diagnostics at the service edge, and then we're going to work to confirm the actual point of presence to not only our own service edge, but the alternate service edge on the other end of the fabric. Once the service edge points are understood, we will then use CFM to show the Ethernet switch path behaviors across the fabric. And this, together with IP diagnostics, will show an end-to-end visibility required by network administrators. So a little review, connectivity fault management is part of the IEEE standard, and it's defined as 802.1 AG. And as we talked about in previous videos, it defines different maintenance hierarchies and different tools to be used within those maintenance hierarchies. We're going to be sticking primarily within the level of 4, which is the SPDM CFM. We will not be using CMAC CFM, although it is part of the actual standards. Instead, what we're going to be doing is demonstrating how we can use IP diagnostics as an overlay function, and we will then coordinate the service point of presence to the network, and then we'll run CFM to actually establish the path behaviors that are happening for that given service. So this is a view of our lab. If you will recall, we installed switch number 4. We still have our console interface through switch number 4. We will telnet to various switches throughout the video in order to run the various diagnostic exercises. But by and large, this is pretty much the framework that we will be implementing our exercises over. Now we're going to start with layer 3 virtual service networks, which, as you will recall, are simply VRFs that are paired together with ISIDs. Now it might seem odd that we're going to start with this higher level protocol architecture first, but this is a native IP service, and it will show how, even though forwarding behavior is not happening over IP routing within the fabric itself, there is a very good and high degree of IP awareness as far as the points of presence are concerned. Now, L3 VSNs can support multicast environments. They're really easy to set up when compared to the traditional VRF IP VPN approaches, and because it's all based on Ethernet, we have a more secure infrastructure due to the fact it's not dependent on underlying IP service topology. So with that, we're going to kind of take a look at what we have in our lab. And as you will recall, we had 2 VRFs. We had a VRF for VidServe, which was the blue VRF. And then we had a VRF for IPTV, which was the red VRF. We're going to be focusing on the blue VRF in this exercise, so we're going to be focusing on VRF VidServe and ISID 5000. Now, the exercise in question is that we are on a certain switch within the infrastructure, and you can see by the slide that we are now on switch 3, and our IP address is 10.50.30.11. And the camera that we're going to is 10.50.10.10, and you can see it's located on switch number 1, and we're going to run IP diagnostics, which will validate the traceroute connectivity and connectivity as a whole across the network. Then we're going to hand it off to CFM and get some further details on what's happening within the fabric architecture. Now, I want to emphasize that we know all of this ahead of time, but we're going to assume that you don't have this detailed information. But we are assuming that you do have access to switch consoles and that you do have access to the fabric's administrative interfaces so that you can gain this service point of information. And that, in tandem with the traditional IP diagnostics at the service edge, will yield us our end-to-end path. So with that, we're going to just escape out of this view here and minimize our screen. And here we have our video surveillance camera, and it's 10.50.10.10. I'm going to, you can see that I'm moving behind the screen. I'm going to open the screen. You can see me. Hello, I'm Ed Kohler. I'm not an automaton. You can tell that I'm a true human being here, and I do have needs, desires, and goals. It's important to have goals. But you can see that this is a live video, and it happens to be in my lab. Now, what we're going to do is we're going to be using this as the service point of presence that we're interested in. And we don't need this interface anymore, so I'm just going to kill it. And you can see that I have two consoles available to me. I have my local command prompt, and then I also have a PuTTY interface into switch number 4, as we've had in the past. So what we're going to do now is we're just going to run an IP config command just to validate the fact that we are who we are. And we can see that we are 10.50.30.11, and our gateway is 10.50.30.1. So yes, the information that we thought is indeed valid. So now what we want to do is run just a simple traceroute command. And we will run that over to 10.50.10.10. As you will recall, that was the video surveillance camera that we were interested in. So we'll just let that command run. Now, I want to emphasize something. You will see that it is one hop away. So we're running over 10.50.30.1, and then we're running directly over the fabric to 10.50.10.1. And from there, we find our point of origin, which is 10.50.10.10. So that gives us our full trace route. It's one hop, but we do know that we're hopping over intermediate switches. We want to understand what those behaviors are. And this is really where the console interface to the switch will come in. So we're into switch number 4. What I want to do is I want to do a show IP route for the vidserv VRF. So it's just VRF vid underscore serve. And we'll take a look at what the route table yields to us. And we can see that, yes, 10.50.10 is here, and it's off of switch number 1. And 10.50.30 is also present, and it is over switch number 3. You'll also note that there are 2 entries for this, and if we kind of extend our table out, we'll see that, and let's just run this command again. You'll see that we're running over the separate backbone VLAN IDs. So this tells me automatically that we're running equal cost multipath. And when I run my trace route, that is exactly what will be validated. So we can already determine that. But there's another way we can gain this information. We can do a show ISIS LSDB TLV 184, realizing that TLV 184 is the TLV that handles L3 VSNs, and we'll say we want a detail of that. And that gives us a different format of information, but still valuable. We can see that switch 1 is indeed holding 10.50.10.0, but we also validate the fact that the VRF ISID is ISID 5000. And we can go down below and see that we are off of switch number 3 as well with 10.50.30. Now, I want to note that if you look at switch number 4 or switch number 2, you'll see that those VRFs are there, but we're not seeing any active 10.networks. The reason why is nothing's plugged in. So the link state database gives us quite a bit of information. We know that 10.50.10 and 10.50.30 are our only active subnets on VRF VidServ, which is on ISID 5000. So quite a bit of diagnostic information can be gained from these tools. Now, the last thing we're going to do, which is almost redundant at this point, is a traceroute command. And given the fact that this is a native IP service, an L3 VSN, we can actually specify the IP address that we're interested in. And as we will recall, it was 10.50.10.10. And we also have to specify that we are in the VRF of vid_serv. And let's just run this command. And we'll see that it will indeed validate that we are using equal cost multipath. And you'll see that the switch, I failed to change my port of entry. I'm coming in through switch number 1. That is not what I'm supposed to be doing. But you can see that we're running between switch number 1 to switch number 4. I am not going to re-record this. This is good enough. So you can see that we're running between switch number 1 to switch number 4. I actually want it to be on switch number 3. So what we're going to do is telnet over to switch number 3. Okay. Now from here, we will enable ourselves, and here we'll run the L2 traceroute command. So from here, we'll run the L2 traceroute. We will utilize IP address variable again. And we will go 10.50.10.10 and VRF vid_serv. And now we'll wait for this trace to release. And the reason why I'm redoing this is we were on switch number 4. Remember, we were consoled in. But remember, I'm located on switch number 3. So I want to know how we're getting to switch number 1 from switch number 3, given the fact that switch number 3 is the point of presence that I'm coming from. So we can see that we have equal cost multipath available. That was validated on the previous command as well when we ran it from switch number 4. As you will see, we have switch number 4, and we ran the command, and it basically gave us 2 paths. But notice how we're using the same path between for both BVIDs. And the reason why is because we only have the single link available between the 2 switches. But here we can see that we have 2 different link paths available, 2 different Ethernet switch paths, and the BVIDs select them accordingly. So we can see that we are indeed running equal cost multipath, and this validates the end-to-end diagnostics between the video surveillance camera and my PC here. So that kind of brings us to the close of the first section. What I'm going to do now is pause, and then we're going to kind of change some of our network topology, and we'll come back to the second piece. Okay, so here we are back. In this section, we're going to cover Layer 2 virtual service networks. And as you will recall, Layer 2 VSN is simply an ISID that is associated with VLANs at the edge. Now, I recommend that you do not put IP addressing on those VLANs, and that yields what's called a stealth Layer 2 network. And there's a number of versions of L2 VSNs. The CVLAN, the switched UNI, the transparent UNI, and the E-tree, or the private VLAN. We're going to be focusing on the CVLAN, the normal subscriber VLAN, in this exercise. Now, when, again, we put no IP addresses on the VLANs, we term the service as a stealth Layer 2 network. Any IP personality is determined by DHCP services within or relayed into that VSN. As a result, any IP relationship to the segment needs to have some considerations. You have to have some topological knowledge. You have to know where your default gateway is located, and you also have to know where you are located. Now, once you have that information, you can take those considerations and then use simple rules to indicate your path forwarding behavior. or you can use IP and CFM tools for a more comprehensive validation, which is what we're going to do in this exercise. So this is a look at the logical topology. We are in a VLAN called VLAN 100, and the ISID is ISID 1000. It takes us one place, and that's a DHCP service, a default gateway, which brings us out to the internet. We're going to run trace routing out to Google, 8.8.4.4, and then we'll utilize path diagnostics to show how we're traversing the actual fabric, which is ISID 1000. So that's kind of what we're going to do in this exercise. As you will recall, we created an ISID 1000 on switch number 4. That's where our default gateway is located, so that's the switch we're directly logged into. And then our system is located off of switch number 2, which is in our IP address is 192.168.1.4. And we are going to validate the path behaviors, which will show that ISID 1000 is traversing across switch number 3 to go between switch number 2 and switch number 4. And that's what this exercise will focus on. So let's move back to our normal console interfaces here. And what we're going to do is just run an IP config to validate the fact that we are indeed 192.168.1.4. And we can see that our gateway is 192.168.1.1. And what I'm going to do now is I'm just going to run a traceroute command, and we'll run it out to 8.8.4.4, which is Google. And let's just let that run. It'll take a little bit to go. Now, we are in switch number 4 here, but really we want to be in switch number 2 because remember, even though our console interface is into switch number 4, my machine, the one I'm using the trace route, is over on switch number 2. So we want to telnet over there. Notice how I can get anywhere I need to within the fabric by the management interfaces. And we will log into switch number 2 and enable ourselves. And okay, we are now in the console interface. And what we're going to do now is we're going to do a show on ISIS LSDB. And we will look at type length value 144, because as we will recall, this is the type length value for L2 VSNs. And what we're interested in is which path ISID 1000 is taking across the network. So I'm just returning all the way down, and let's just scroll up. And what we're looking for is an entry of where ISID 1000 has an entry of both. So as you can see, 1001 has the entry of both, and that's showing that it's going over the primary BVID, and that's the way it should be. Odd always goes over the primary, and then even goes over the secondary. So our secondary BVID is 4052, and we can see that ISID 1000 does have an entry for both, and we're looking at switch number 4 in particular, but it really doesn't matter. This is going to be the same consistently across. So we know that ISID 1000 is going over BVID 4052. Now, we can also see that we've completed our trace route from an IP diagnostics perspective, and that took us out across the network, and as you can see, trace route looks quite normal. We went out across the Northeast Roadrunner backbone, we went into T-Bone, and from there we went into the T-Core, and that's where my Google DNS-B location is, at least the nearest one for me. So here we go. This shows that it really does give us the detail we need. What we're interested in is this first hop. What's happening between 192.168.1.4 and the default gateway. And that's exactly what we're going to look at here. Now, it's easy enough to do at this point. We can just do a layer 2 trace route. And with that, we are going to specify the VLAN that we're interested in. We know that that is 4052 because we know that that is the path that ISID 1000 is taking. And now that's all we're going to do is specify our router node name, which we know is switch number 4. And we'll let that diagnostic run out. And you can see that it is indeed confirmed that it is traversing over switch number 3. So going back to our previous slide, we see that between switch number 2 to switch number 4, we are traversing the predicted path for the secondary BDID, which is 4052, and that is through switch number 3. So we now have a complete train of diagnostics for the end-to-end path using IP traceroute and the traceroute facilities within the fabric itself. So let's kind of do a summary here. By using service point of presence information for IP, we can use IP and CFM diagnostics in a very complementary fashion. IP service types, such as L3 VSNs, can be enumerated with IP route tables or the ISIS link state database. And then we can use CFM to confirm the path behaviors within the fabric as a result. Stealth L2 service types require a little bit more information because we need to know the service points of presence as far as where the default gateway is and where your diagnostic ingress is happening. But that can be easily gained from just knowledge of the network and even the link state database, as we've shown within the video. From there, simple tiebreaker rules using the even and odd ISID rules with the primary and secondary BDID will indicate the service path behaviors. Or we can use CFM, and we can then use that to confirm the actual path behaviors in an actuary fashion. So that's pretty much it. I hope you enjoyed the video. Do try this in a lab. I think you'll find it fascinating, particularly with more complex topologies. Thanks a lot for watching, and stay tuned for another one coming up. The next video is going to focus a little bit more of a deeper dive on stealth networking design. Thanks for your time.